My name is Earl Ruby, and we're going to talk about using AI without GPUs today. And hopefully my clicker is actually working. Nope. I'm going to have to do this manually then. Um, so I originally joined a small company called Bitfusion a couple years ago, and we were doing disaggregated GPUs for AI ML. We got bought by VMware, and then VMware just recently got bought by Broadcom. So now we're VMware by Broadcom. Throughout that time, I've been working on various AI ML accelerators at Broadcom and making sure that they work with vSphere. So about a year ago, I started looking at the Intel hardware and seeing what we could do with it on vSphere, making sure that everything was working, so that you could use the full capabilities of your Intel hardware with vSphere. So today I'm going to talk a bit about private AI with Intel. I'm going to talk about Intel AMX CPUs, configuring vSphere to use those CPUs and instructions. And then I'm going to run some LLMs on CPU only, no GPUs involved, and point you to some resources. I actually have two talks today, so when this one finishes, there's another one coming up right after. So first of all, VMware announced private AI with Intel back in Barcelona a couple months ago, and this represents a commitment by VMware to support AI workloads running on vSphere, running on Intel hardware. So we want to run those on premises in your own data center privately. You're not sending any of your data out anywhere. You're not sharing your data with third-party APIs. Keeps everything on site. You want to make sure that you can minimize intellectual property risk. You can ensure that your data is not being shared anywhere externally, and you can have complete control over who is accessing your AI models because it's in your data center. Areas such as privacy, data protection, security, resiliency, these are all core to the private AI vision and the associated products that we will be launching. So since it's vSphere, you've got the same trusted security tools that come with vSphere also work to secure your AI workloads. Because you're running vSphere, you're also getting things like secure boot, virtual TPM, vSphere trust authority, VM encryption, things like that. You're getting the ability security using established identity manager products. You're getting network security provided by NSX, including their microsegmentation and advanced threat protection. And the best part about deploying AI workloads on CPUs is that you already have clusters of CPUs. So Intel has an AI software suite that is optimized for Intel CPU hardware. They provide the same open source tools you're already using, and they've been optimized for Intel CPUs. The changes are upstreamed to the tools open source repos. So the optimizations are becoming part of the open source repository. So you're running Intel stuff that's been optimized, but it's the same open source tools you use everywhere else, and without making any changes. So before I start the technical part of the talk, I do want to let people know that I'll be listing some URLs on the screen, and I'm also going to show some QR codes when I have those URLs listed. So if you want to take a screenshot or something, grab a screenshot. It'll take you to a QR code. Will take you to the URL of the thing I'm talking about. That way you can try some of the stuff out yourself. So the streaming audience, if you want to try these things out yourself, you can. YouTube audience, same thing. Grab the QR codes. So about a year ago, I was asked to take a look at the new Intel hardware, the Sapphire Rapids that had just come out for CPUs. And I was looking at this thing called AMX, Advanced Matrix Extensions. So this is a new set of instructions. They're built right into the chip. They're designed to work on matrices to accelerate artificial intelligence and machine learning related workloads. The advanced matrix multipliers are integrated into every core. And if you purchase Sapphire Rapids or Emerald Rapids servers, you can run AI workloads on the CPUs without a separate GPU accelerator. AMX works with frameworks such as PyTorch, TensorFlow, PaddlePaddle, OpenVINO, and vSphere 8 supports Intel AMX. And so, as I'm sure everyone here knows, GPUs are just specialized matrix processors. They can perform mathematical operations in parallel on matrices of numbers. And although GPUs were originally designed for graphics, turns out working on matrices is very useful for AI ML. And AMX was introduced by Intel in June of 2020. It was first supported by Intel with the Sapphire Rapids microarchitecture for Xeon servers. It introduced three-dimensional registers called tiles, which accelerators can perform operations. It is intended as an extensible architecture. So the first accelerator that was implemented is called the Matrix Multiply Unit, or TMUL. Data comes directly into the tiles, while at the same time the host hops ahead, dispatches the loads for the tiles. The TMUL operates on the data the moment it's ready. At the end of each multiplication round, the tiles move the cache and single instruction, multiple data, SIMD post-processing and storing. So SIMD is a form of parallel processing, enables the processing of multiple data sets, multiple data with a single instruction. So the goal of the software is to make sure that both the host and the AMX unit are running simultaneously to maximize the throughput and performance. And one of the creators of this architecture, Bob Valentine, was saying, hey, we can do good inference on Skylake. We added instructions in Cooper Lake and Ice Lake and Cascade Lake, but AMX is a big leap, including for training. And the idea here is that as you replace, as customers replace older hosts with Sapphire Rapids-based hosts or Emerald Rapids-based hosts, they not only get the performance improvements for traditional computing, but they also get AMX capabilities for AI/ML. So you can execute diverse AI and non-AI workloads on the same hardware side by side in a virtualized environment. You get the flexibility to repurpose the IT infrastructure for AI and non-AI use as demand requires without additional spending. And because Xeon and vSphere on-prem in cloud environments is pretty ubiquitous, and you've got this optimized AI software stack, you can quickly scale the compute in hybrid environments. Your customers can run their entire end-to-end AI pipeline, data prep, training, optimization, inference with CPUs using built-in AI accelerators. Because it's running on vSphere, you're getting bare metal-like performance with vSphere. The open source AI software that Intel is accelerating these workloads. There's a unified software stack for CPU and GPU called One API. So if you're using the One API stack, you can, and you do end up adding GPUs, you can run the same software, the same workloads, just get even more acceleration. And then, like I said, most of the open source data prep, machine learning, and deep learning frameworks are optimized already for Intel CPUs. You can use the same tools you already use. Nobody has to change their tool sets.
Does all of this require vSphere 8? Because I know lots of different AI workloads could run on vSphere and get close to bare metal, depending on.
So since AMX is a new instruction, and vSphere is a virtualized environment, so we have a thing called the hardware version, which is I was about to talk about, but I'll talk to your point. So the hardware version determines what instructions are virtualized, and vSphere 7 goes up to hardware version 19, and AMX is included in hardware version 20. That's why you need vSphere 8. So, which pretty much the slider here that I'm about to talk about. So yeah, so the requirements are to actually run this in your environment, you need Sapphire Rapids or Emerald Rapids CPUs, obviously. Your guest VMs need to be running Linux with a 5.16 kernel or later, 5.19 recommended. You've got to be running vSphere 8 OU2 and vCenter 8 OU2. And then guest VMs are using hardware version 20. Once you've got all that, the AMX instructions are there in the VM. If you're running software in the VM, it's going to be able to use those instructions, and you can do your AI workloads that use AMX. So if you want to go look for the tools, there's a...
Do you find any reduction in, application? I'm not sure how to answer the question. How application use of vCPUs when AMX is enabled? I mean, are you seeing some different workload constraints when AMX is enabled?
Different workload constraints. I'm not sure quite understand.
How many applications can run on
I see what you're
real
saying.
hardware environment?
Yeah. So I've got some slides later on where I show what we're doing, what we've tried so far. and how far what we've done to show that this works. I'm working on a cluster right now where I'm actually going to be running scale tests, where I can say, okay, if I run this workload one time with this many vCPUs, what kind of performance do I get? If I run 100 copies of it, what kind of performance do I get? And scale up, and then kind of chart out and see where does the performance start to degrade. You know, at some point, performance is going to degrade. We just don't quite know where. We haven't actually done the large scale tests yet. But I'll show you some demos later on what we have done, and you can kind of get an idea. The Intel AI tools selector, by the way, this is a link to Intel's website. They've got all of their tools that they are working on, that they have optimized for this technology there. They are upstreaming those changes too, like I said. So if they come up with a change for PyTorch, for instance, that's going to accelerate your workloads on PyTorch, you can find the latest version on Intel's website, but those changes are being upstreamed. And eventually they will be in all the open source packages. So if you want the latest tools for AMX, go to the Intel site, but just rest assured all of those changes are getting upstreamed, and they will become part of standard packages. Sometimes it lags a little bit. So I tell people, go there, keep your tools up to date if you want the latest versions. And this is like a screenshot of the actual tool selector page where you can actually download things and get all your popular tools for AMX. When we first started looking at this, I was going, well, let's try to run some LLMs on this, but we wanted a comparison. So I took an old Ice Lake system, and on the Ice Lake system, this was a system that entered our AI lab maybe 4 years ago. So it's running Ice Lake CPUs, no AMX at all. And I fired up a VM and loaded a container on that VM. That container's got an LLM in it. The LLM is Hugging Face 7 billion parameter model. And as I said, the Ice Lake was a upper mid-range server when I bought it about 4 years ago. But you can see it's taking a while just to even load. It's getting this loading checkpoint shards, 0%. It's kind of chugging along, not moving along very quickly.
How many parameters did you say it was?
I'm sorry?
How many parameters did you say it was?
7 billion.
Thank you.
And it takes about a minute to load everything and introduce itself as a large language model. That's 50% done loading. And it's just kind of showing, okay, finally got it. It's finished loading the tokenizer. Now it's coming down here. Eventually it's going to spit out that it's a large language model, and how can I help you, sorts of thing. And I start asking it to help me write a story. So up there it goes. Finally, welcome to. So you can see it's working, but it's really slow, and it's not. This is not acceptable. It's the latency is way too slow. So not really doing what you want. And if you were to try to use this in production, obviously that's not going to be fast enough. And this is why a few years ago, why everyone wanted to use GPUs, because this isn't going to work for most people. And come on, say it, state of the art. I am a state of the art language model. Come on, there we go.
I love the.
There we go.
I love the. You're helping us feel the pain.
Yeah.
Of the.
You can see I just started the Sapphire over here on Sapphire Rapids. Same exact container, same model, same everything, and it's already ready to go. It's finished. It's going to help you already. And that's just flying past the Ice Lake. And so, like I said, same 7 billion parameter model, same container, same everything, except just two different pieces of hardware, and no GPUs anywhere to be found.
So how hard is it working the CPU at that point? Like if we saw an activity monitor or something similar, is that like 100% core saturation to generate that level of performance out of the Sapphire Rapids?
Let's memory.
This one, I'm trying to see. Let me see if I've got that written down here. I think we were using. I don't have that listed. I'd have to go back and I'm trying to remember. I think this was we're using 56 vCPUs and like 64 gigs of RAM. But that was just like we just threw it on that. It could probably use less. Not sure.
Gotcha. But to do that level of inferencing, was it saturating all of those 56 CPU cores, and what did the memory look like at the same time? Do you have that data?
CPU utilization stuff.
Yeah, exactly.
Yeah, I actually don't have it for this particular demo, so I can find out. I can find out for you. As I said, what I really like, what I'm starting to do now is the scale testing and the like. How little hardware can you get by with to run these models? Because that's what you really need to know for scale. So, and I've got that in a later demo actually, where I really scaled down and just to see how low it could go, and I was kind of stunned how low you could go. So
that wasn't lost.
So Earl,
That's just me.
the prior presentation, we talked about upstream changes for Intel, Intel extensions, and Intel tools. Are you using any of the extensions or tools in this solution, or just using the upstream support?
In this one, we were using this was the model itself was optimized for AMX, so it was run through it was OpenVINO to optimize it for AMX. But it's just the model was just downloaded straight from Hugging Face, so not.
So you're not using any special extensions in the
No.
implementation of
On this one. Yeah, this was straight from Hugging Face.
Why'd you point at me?
And come on, next slide.
Don't hit me.
Here we go. So actually, I'm going to skip that one. I'm going to talk about LLM fine tuning. So that last demo, that was just off the shelf, no fine tuning, no nothing else. So we thought, hey, can we fine tune a model? So we took once again vSphere 8 with Tanzu, Sapphire Rapids with AMX. We used Converge.io to build and automate the machine learning. So we were running it on a 4-node Kubernetes cluster. We picked a Llama 2 7 billion parameter model and a finance alpaca data set, which is it's about 17,500 queries of finance data. So we took basically a generic off-the-shelf language model, can speak to in English, wanted to train it with a finance alpaca data set to fine tune it. Took about 3 hours and 33 minutes to fine tune on CPUs only, no GPUs involved. And that was on a 4-node cluster. So if you've got compute around and you want to fine tune it, you can do that. And then once we fine tune it, we can actually run it. And so here we're actually running it, and these are actually running on a single. I know it's a 4-node system, but we're actually running these on a single node of the 4-node system. So we've got 3 chatbots running here. We're going to take the LM that we just fine-tuned. It's got financial data. All 3 chatbots are running on a single Sapphire Rapids Xeon 4 host machine. You can now ask it things like, what is IRR? And it starts to tell you what is NPV. It starts to tell you net present value down here. What's the difference between IRR and NPV?
In this case, it's not a RAG augmented solution. It's just the basic LLM with fine-tuning on the finance model.
Yeah. So we basically, in 3.5 hours, we've created a chatbot that can talk to you about finance using off-the-shelf components. And once you've done the fine-tuning once, it's ready. If it's good enough, it's ready to go.
No GPUs,
no GPUs. This is all CPU.
And these are all talking to the one node, or is this one-to-one?
This is actually running on one node of that cluster. We used a 4-node cluster to train them. We actually ran it. They're actually running on one node.
Okay.
So not saturated. And then people start saying, well, when should we use GPUs? When should we use CPUs? And I always tell people, use CPUs when you can, use GPUs when you must. So if performance is good enough for your use case, such as inferencing, CPU. If you're batch processing ML workloads, like the fine tuning we just did, if it's LLM with less than 15 to 20 billion parameters, you can do it on CPUs. If you're going to keep operating costs down, is a higher priority than getting immediate responses. CPUs, like even our last person, Keith was talking about when he was up here talking. Power becomes a constraint, sustainability becomes a focus. Use CPUs. And I want to comment on that last one. If you've got GPUs that are sitting idle, they're still sucking up quite a bit of power. If you are fully utilizing your GPUs, like they are maxed out all the time, 24/7, you use a lot of power, but it's actually a little more efficient than CPUs. But if you're not using them all the time, if they're sitting idle a lot of the time, you're probably using more power than you would if you just ran the workloads on your CPU infrastructure.
So Earl, I'm sorry, before we get into when to use GPUs, we hinted to this in some of the two earlier presentations, but we really didn't talk about the operational impact of going from CPUs to GPUs. Uh, Ro had a slide where it talks about kind of general, like that intense, always on, we're training models, you have to build GPU clusters, et cetera,
Sure.
dedicated to that use case.
Yeah.
And we're not doing that, then the general purpose CPUs are a factor. What we didn't capture in that conversation, the conversation was mainly focused on compute. We didn't actually talk about like networking, storage, and all the other requirements to build a environment that takes full advantage of GPUs. Have you folks done any data or research around the operational impact of building for that extreme use case versus general compute?
Yeah, it really depends on the use case. And we have customers coming to us with this same question, like, and we would say, well, what's your use case? How much data? How much network? Because there's so much variation depending on the application. So it's hard to come up with an off-the-shelf answer. So I have this idea of like, hey, why don't we just build a cluster? We'll figure out. We will run a model on it, set the parameters, measure latency, measure throughput, measure all the things that you want to measure it all automatically. So you can basically just launch a container, it runs, it grabs all the measurement data, collects it, done. Okay, now let's change a couple of those parameters and run it again. How does the performance change? Let's scale it up. How does the performance change? Let's scale it up some more. How does the performance change? And by running just a set of experiments, we can model and figure out exactly. With the modeling, we should be able to figure out, okay, depending on your application, if you're trying to scale to this, if you're trying to use this type of model and you're scaling like so, this is how much hardware you're going to need to run that efficiently. That
Yeah, it's a lot. It seems like there's a lot of opportunity for research in this area of helping customers understand the overall TCO of moving to GPUs to CPUs when you actually get your inference into production.
Correct.
It seems like a pretty interesting.
And it's a question that comes up over and over, and there isn't much good data on it. A lot of it is trial and error. A lot of it is like, try it and see, and does this work for your use case? So we'd really like to have more hard data on.
You mentioned, yeah,
Exactly that.
You mentioned fine tuning and inferencing here. I'm trying to understand how that would be applicable to, generating a RAG or something like that, where you're taking, a corporate corpus and building a vector database through embeddings and all that stuff. And then once it's built, you're using the vector database to provide context to the LLM. I mean, is it something that you think might be applicable to CPUs or?
Yes. Oh yeah. Yeah.
You said yes?
Yes. I think that's applicable to CPUs.
Do you have any information or details on trying that, or?
I know one of the people that I work with has been working with that, but I don't know what his results are yet. We are looking heavily at RAG. Once your RAG data is in the vector database, it doesn't actually. I mean, it's just a database. You're running on CPU. It's storage.
I understand that, but the big challenge is it's like fine tuning. It's getting the data into the vector database.
Yeah. So once it's in,
it might be applicable to CPU searching solution.
Correct. So it's still early days for that, and for us, RAG. But yeah, Stay tuned.
Oh, yeah.
Be publishing more papers in the future. And then we also talked about latency earlier too. We were talking about how quickly can it respond, and that's the big difference between CPUs and GPUs. You're going to get lower latency with a GPU. So if low latency and immediate responses are critical, GPUs are probably the way you want to go. If you're comfortable with a little bit of a lag, CPUs are fine. If you're fine-tuning a model with more than 15 to 20 billion parameters, if you're frequently fine-tuning large models or frequently building large models, you're going to want to use GPUs. And if you just need more performance than you're getting from CPUs, you're going to want to use GPUs. And as I said, we're trying to actually put some numbers behind that so you can see exactly when to use each one. But we'll publish things as we come up with them. And so some things to take away from today's talk. Think about VMware Private AI with Intel as a solution for enterprise. Today's CPUs are AI aware. You can do things with Sapphire Rapids and Emerald Rapids CPUs that used to require GPUs. And Private AI allows you to keep your data and intellectual property on premises. And I've got there's another QR code coming up. That takes you to our AI ML webpage with links to all of the various papers and information about Private AI. Yeah, thank you.